So the last two simple machines to discuss in 4.3 are the inclined plane and wedges. Inclined plane and wedges actually act almost the same way. So as you see here, an inclined plane is really just going to be like a ramp, right? Ramp is what we call them in everyday talk, but that's technically an inclined plane. To figure out the mechanical advantage, you divide the distance that you're going to travel up the ramp and divide it by the height. Right? So you're going to divide the length of the plane by the height of the plane, and that will give you mechanical advantage. And this makes sense because what you want to do is you want to make this longer. The longer you make that ramp compared to this height, the more mechanical advantage you will have. So in order to make this ramp better, quote unquote, right, a greater mechanical advantage, they would actually take it and have it be this long, right? So the angle that it would be traveling at would be a shorter angle, and it would travel a lot further. So that means that the length, rather than being 3 meters, might be 6 meters compared to 0.6, and then the mechanical advantage would go from 5 up to 10, right, if you could double the length of that ramp. And again, this is just playing with that force-distance trade-off. Okay, so a wedge works the same way. A wedge is like a knife, doorstop, plow, axe, or a chisel. So I'm going to kind of pop down to this picture here. Oh, I forgot about screws. We got one more. So this wedge should look very similar to a ramp, right? Just like connect it with another side, and now you've got your ramp turns into a wedge. But what you're going to do here to find your mechanical advantage, you're going to divide the length by the thickness. Hey, wait a second. Thickness, aren't we just calling something that we previously called height as thickness? Well, since now this is a three-sided object, 1, 2, 3 sides, and right here we just had 1 and 2, that we could actually call height. This is going to be thickness too, because it's measuring from this side of it to this side of it. That will be your thickness. But essentially you calculate the mechanical advantage of a wedge in exactly the same way as you do for an inclined plane. So these are, I'm going to connect those two because they're very similar. Essentially, if you're going to pretend like this is an axe head, right, if you sharpen it, that's going to make this thinner. That's going to make this piece here longer, and that's going to make this piece here longer. The sharper and sharper you make it, decreasing the thickness, the sharper you make it, it will be a lot thinner, right? That thickness will go down. It could go down, if you really, really sharpen it out, it'll go down from 2 centimeters down to 1 centimeter, which would double this mechanical advantage to 8, right? 8 divided by 1 rather than 8 divided by 2. So, sorry, before I said you're making this longer, that's not true. You're just making it thinner, right? You're making it thinner. So a screw is something we already talked about, right? Here's my wonderful picture of a screw that's going to go into a wall, and you've got those little twists around it. Once again, you divide the length by the thickness. So the length of that is going to be, you take that swivel, if we go like this, right, here's that swivel, the actual screw, the grooves, right, if we took that and then we stretch that out, it would actually be this long, right? So let's say that's 10 centimeters, but you're dividing it again by the thickness of this screw head right here, right, which is probably like that thickness here is like probably 0.2 centimeters. So you've got something like that, 10 centimeters divided by 0.2 centimeters. That's going to be a huge mechanical advantage. So MA will once again be the length by the thickness. So this is just another example of how, essentially a screw is an inclined plane wrapped in a spiral around a cylinder. So really what we're talking about here is the same thing that we were talking about right here. You make this piece longer by increasing the number of those ridges, by increasing the number of those grooves, and the longer it gets, the greater this number will be compared to the thickness, how thick it is right here, and that's going to give you a greater mechanical advantage. You're going to have to be twisting it for longer, but each of those twists will be a very small amount of force, but it will hold in the wood that you've screwed it into with a really strong hold. So you make a screw better, or you make a ramp better, right, an inclined plane or a wedge better by making it longer and thinner, right? So you can decrease this height here, you can increase this length. You can increase this length, right, out to here, or you can make this piece here thinner. Here you could make this a little bit thinner, or by making these, by adding more grooves onto it and therefore making it longer. Because we're always talking about length versus thickness. For ramps, we call it height, but same idea. The final piece we're going to talk about is compound machines. Really, compound machines are going to be two or more simple machines working together. So in this one, in this can opener here, we've got wedges right here, right, on the blade of the actual can opener. We've got second-class levers right here that are going to be pulling together and clamping the blade that's down here and the blade that's here, clamping those closer together. And right in here, you've got the wheel and axle. You spin that outer wheel, right? You spin it around. And right in here, you've got a tiny little axle that then spins with much greater force than you were applying to the handle. However, here, the mechanical efficiency, while the mechanical advantage might be greater, right? Because you've got all these different machines working together. Each one of them is going to be multiplying the mechanical advantage, is going to be multiplying the output force. However, the mechanical efficiency is going to be relatively low because there's lots of friction due to all the moving parts, right? There's moving pieces of these two second-class levers coming together. There's moving pieces in between the wheel out here and the axle in here. These two blades have to be moving against either kind of side of the top of the can. These gears in here are going to be twisting and grinding against each other. So all of those different pieces that are moving against each other is going to create a lot of friction. So while the mechanical advantage will be much greater, for instance, you try and open up that can without a can opener or without a blade of some sort. It's not going to happen. You can't, with your hands, create enough force, especially without cutting yourself, but without enough force to open up that can. However, this tool has a much greater mechanical advantage. However, a lot of the force that is generated by the wheel and axle, by the second-class lever, and the wedge is spent overcoming friction. So it still has much greater mechanical advantage, much greater force than your hands, for example. However, some of the force is lost to overcoming friction. So this kind of gets back to that 4.2 video talking about mechanical advantage versus mechanical efficiency. So if you're confused on how those two are different, you should check them out. Remember that this one has to do with force, and this one has to do with work. So you can still have a greater, a great mechanical advantage of 10 maybe, right? It multiplies the force by 10. However, some of that force is going to be spent overcoming friction, which means that it's not actually doing as much work on the object as you want because some of the force is being wasted, right? It's being just sent off to dealing with friction. So still a good tool, but not totally efficient, right? So to kind of wrap up 4.3, we've gone through, compound machines, which is just a combination of the other 6 machines. So we've got screws, wedges, and I'm actually going to kind of combine this up here. Screws, wedges, and inclined planes, which are all very, very similar and work in this same fashion. We've got a wheel and axle. You turn the larger wheel, it moves a small axle, thereby multiplying the force. We've got 3 different types of pulleys. One of them just changes direction. Another one doesn't change direction, but multiplies the force by 2. And this one changes direction and multiplies the force by the number of rope segments, essentially the number of pulleys. Then we've got 3 different classes of levers. This is probably the confusing one. The 3 different classes of levers, we've got first class, which is the fulcrum in the middle. We've got second class, which is the fulcrum with the load in the middle. That's a wheelbarrow. And the third class, which is your bicep or a hammer, we've got the input force in the middle and the load, the output force, on the side. So this is the hammer example. This is the wheelbarrow example. And this is the can opener example. Or sorry, not can opener, is the paint can opener. Right? So if you generally think about first class levers as this, second class as wheelbarrow, and third class as the hammer, that will at least get your mind thinking about an actual example, and then from there you can figure out where the fulcrum is, where the input and output forces are. Within first-class levers, you can change the mechanical advantage by moving this fulcrum around. Closer to the load or closer to the input force will increase or decrease the mechanical advantage. So for each of these 6 simple machines, we should generally know if they change the direction, right? So first-class levers do change the directions, second-class levers do not, and third-class levers do not. They all move in the same direction for second and third class. We should also know how to go about calculating the mechanical efficiency for each of these different simple machines. Please let me know if you've got any questions. This is the second video of 4.3 types of machines.